Hello, in this video I'm going to explain the solution for question number 6 in the permeability, seepage and flow net problem set. So this question talks about a seepage scenario. So the required information for the calculation and also the drawn flow net diagram is given. As you can see here, there is a sheet pile driven into a silty sand, and on your left hand side it's a upstream side, so there's a higher head exists there, and then towards the excavation water flows from left to the right. The given flow net diagram, you can see all the equipotential lines as well as the flow lines that you will need for your calculation. The part A of the question asks you to calculate the seepage flow rate under the sheet pile. To calculate the seepage flow rate, we are going to use that equation Q equals KH times NF divided by ND. If you look at different terms in this equation, simple K is the seepage flow rate, and K is the permeability of the soil, which should be a known parameter, and H is the total head difference between the upstream side and the downstream side. NF is the number of flow channels in the flow net diagram, and ND is the number of equipotential head drops in the flow net diagram. So the equipotential lines and the flow lines are the two types of lines that you can find in a flow net diagram. And for this question, the permeability of the soil or the hydraulic conductivity is given, which is 1.8 times 10 to the power minus 5, and simple H is the total head difference between upstream side and downstream side. So we can determine the total head at upstream boundary. So the total head comprises with, for seepage problems, two parts: pressure head plus elevation head. So the pressure head at the upstream boundary is the the height of the water above the upstream boundary level. You can see 1.25 meter height water is there at the upstream boundary. So that will be 1.25 upstream boundary, and plus the elevation head. So elevation head we measure from a reference level, which we call the datum. So the datum can be considered at any horizontal level. So if you consider the datum level as the level at the excavation base, you have a 2.5 meter elevation head to the upstream boundary. So I took the datum as the excavation bottom, excavation base. Similarly, we can calculate the total head at downstream boundary. For seepage, it is the pressure head plus elevation head. So the pressure head is the height of the water above the boundary level. So we can see that within the excavation there is no water, therefore the pressure head is 0. And elevation head is the height above the reference level, which is the datum. So you can see that we assume the datum as the excavation base, which is the downstream boundary. Therefore your elevation head is also 0. Therefore the total head difference will be 3.75 at the upstream boundary minus 0 at the downstream boundary, which will be 3.75 meter. So we substitute 3.75 here, and then NF and ND. So the NF is the number of flow channels. So you have to refer to the flow net diagram in order to get the NF and ND values. So if you look at the flow net diagram, you can see that there are several flow channels, and so the best point to calculate the number of flow channels is underneath the sheet pile wall. So you can see underneath the sheet pile wall there are 6 complete number of flow channels plus another bit. So that bit you have to estimate how much it from a complete flow channel. So I would take it as 6.2, 6 complete flow channels plus a fraction of the next flow channel, which can be estimated as 0.2 of a complete flow channel. And then you have to calculate the number of equipotential head drops. You can see that your first equipotential line at the upstream boundary is the upstream boundary itself, and then from there to the next equipotential head drop, that will be a 1 head drop. Likewise, you can count the total number of head drops until the downstream boundary. If you calculate the total number of head drops like that, you will end up with a value of 14. So that will be your ND value. So from this we can easily calculate the seepage flow rate, which will come out as 0.108 cubic meters per hour per meter length. So we are considering a 1 meter length of the sheet pile wall, therefore it is per 1 meter. But the question asks you to give the value, the final value, in the units of liters per hour per meter. So therefore, if you convert this one into liters, that will be 108 liters per hour per meter length, 1 meter length. So we are looking at a 1 meter length. So this is because this is just the cross section of the sheet pile wall. So that will be the answer for part A. Part B of the question asks you to calculate the factor of safety against a piping failure or against a quick condition, which are the same. So to calculate the factor of safety against a piping or a quick condition, so we need to focus on the exit square. So because the exit square is the most probable location for a quick condition or a piping failure to occur. So you can see in the flow net diagram, the exit square is shaded. So you have to calculate the factor of safety against a piping failure considering that exit square. For the exit square, so to calculate the factor of safety, we are going to use this equation. Factor of safety against a quick condition is the critical hydraulic gradient divided by the actual hydraulic gradient. So the critical hydraulic gradient depends on the densities or the unit weight of the soil and unit weight of water. So the critical hydraulic gradient is defined as density of saturated soil minus density of water divided by density of water. So you can see it is independent of the flow net diagram or this situation. So it is about the saturated density of the soil available. So you can see the densities are given. So the density of the soil given as 1850 and the density of water is always 1000 divided by 1000. So that will be 0.85 is your critical hydraulic gradient. And the other thing you need to calculate is the actual hydraulic gradient for the exit square. So the actual hydraulic gradient is defined as the head difference divided by the length. So the head difference across the exit square is the difference between total head between the two equipotential lines that the exit square covers. So the total head difference between any two equipotential line is the same. That's why they are called equipotential lines. So the total head difference across the total number of equipotential lines is the total head difference between the upstream and downstream, which we calculated as 3.75, and then we calculated we have 14 number of total equipotential head drops. Therefore, per one equipotential head drop, there will be 3.75 divided by 14 head drop. So therefore, that is common for any two equipotential head drops. So therefore, across the exit square also, the head drop is 3.75 divided by 14, and the length of the exit square, so which you usually have to measure it from, since this is a scale drawing, you have to use the scale to measure this up. However, for this question, that length is measured as 0.5 meter, and since this kind of flow net diagrams are scale diagrams, so you can simply measure it from your ruler and then scale it up to the correct scale. And now this your actual hydraulic gradient will be 0.536. Now you can calculate your factor of safety against a piping failure, which will be 0.85 divided by 0.536. which will be 1.59. So we are expecting at least about 1.5. So it satisfies the requirement. So that is the factor of safety against a piping failure or a quick condition. Part C of this question asks you to calculate the effective stress at a given point A, which is within the downstream side of the soil. To calculate the effective stress, we know that we need to use the effective stress law. For part C, therefore, first we need to use the effective stress law. Any effective stress is equal to the total stress minus pore water pressure. So therefore, in order to calculate the effective stress at point A, we first need to calculate the total stress at point A and then the pore water pressure, and the difference will be the effective stress. To follow that approach, first we need to calculate the total stress, which is sigma at point A. So as per the diagram, you can see that point A is 1.88 meter below the downstream side, the downstream boundary. So therefore, we can calculate the total stress as gamma saturated times Z. So the saturated unit weight of the soil, what the given value is the density of the soil. From that you should be able to calculate the saturated unit weight. The density is 1850, so you need to multiply that one by 9.81 and then divide it by 1000 to make it in the units of kilonewton per cubic meter, and multiplied by Z. So Z is our 1.88. So that will be 34.1 kilopascal. So your total stress at point A is 34.1 kilopascal. So we just used only the saturated unit weight of the soil plus the height of the soil above point A level. Now to calculate the pore water pressure, the second part pore water pressure, we need to use the information from the flow net diagram. So first what we could calculate is the total head at point A. Total head at A. To calculate the total head at A, so we know that the total head at the downstream boundary we can calculate, and then from that we can determine the total head at point A. So for that we need to now define a datum again. So I will take the horizontal level that goes through point A as the datum. So to calculate the total head at point A, so first we need the total head at downstream boundary. So the pressure head at the downstream boundary is 0 because there is no water above the downstream boundary level. However, there is an elevation head because we considered the datum level as the horizontal level that goes through point A, so which is 1.88 meter below the downstream boundary. So that will be your total head at downstream boundary. And now to calculate the total head at point A, so we know that the head decreases, the total head decreases from upstream boundary towards the downstream boundary. So in the opposite direction, therefore, from the downstream boundary towards upstream boundary, the total head increases. So at the downstream boundary, you have 1.88 meter total head. So there should be another component come from the flow that we can calculate from the flow net diagram. So up to point A, we can calculate the number of equipotential head drops we have. And if you look at the flow net diagram, we can see that there are around 4.8 number of equipotential head drops. So 4 complete head drops plus almost another complete head drop. So that will be altogether 4.8 head drops, and then per each head drop we know that the head drop is 3.75 divided by 14. So that will be the total head difference between any two equipotential lines. and then we have 4.8 number of those. Since we are calculating from the downstream side, it has to be added to the downstream total head. So we could have done the other way from the upstream side as well. So you could have calculated the total head at upstream boundary and then deduct the number of equipotential head drops to the point A multiplied by the same value. That could have given you the same answer. So therefore this will be the total head will be 3.17 meter. So now you can calculate the pressure head at A. So the total head comprises with the pressure head plus elevation head. Therefore the pressure head is the total head minus elevation head. So the total head is 3.17 minus the elevation head. Remember, I used the datum as the horizontal level that goes through point A. So therefore at point A the elevation head is 0 because it coincides with the datum. So therefore your elevation head is 0. So your pressure head is 3.17. So once you know the pressure head, you can calculate the pore water pressure. Pore water pressure at A. So basically pressure head means the pore water pressure divided by the unit weight of water. So therefore your pore water pressure is pressure head multiplied by the unit weight of water, which is 3.17 multiplied by 9.81. So which will give you 31.1 kilopascal. So that is your pore water pressure. So now you can use the effective stress law equation. The effective stress equals total stress minus pore water pressure. We have calculated the total stress as well as the pore water pressure. So therefore your effective stress sigma dash at point A equals the total stress that we calculated as 34.1 minus the pore water pressure is 31.1. That will be 3 kilopascal. So 3 kilopascal is the effective stress at point A. That is the answer for part C.